How's it going, Algebra 1? It's Mr. Knight, and we are going to try to do substitution once again. I think now that we've kind of gotten literal equations a little bit more under our belt, and we have an idea of how equations should be solved, and what it means to solve for a variable, I think we're ready to go ahead and give this another shot. What do you say? Let's do it. You don't have any say. We're doing it, ladies and gentlemen. Let's go right in, okay? Substitution, if you need some kind of definition, it's really just about replacing a variable with an equal value or an expression. So if you recall, if we're solving an equation like 2x equals 6, we know that x is going to equal 3. And what we could do is, and what we can say is, we could say that x is solved for 3 because x is by itself and x is equal to something. So x equals 3. And we can actually replace or substitute x with 3 in the equation. And we would do this to check and see if this was true. And obviously, we know it's true. 2 times 3 does equal 6, okay? So we're going to extend this idea, but with system of equations. So this is an example of a system of equations. Basically, that just means more than one equation. And these equations are related because they both have an x variable and they both have a y variable. So because they share an x and y variable in common, if we were able to solve for x, then we could use that same x for both of these equations and then solve for y, or vice versa. We could also write our solution as an xy ordered pair. This is kind of going back to when we graph them, but typically, just in general, as is etiquette, we write it as an ordered pair, x comma y. And there's two types of systems, and we're going to work with the first one just for a little bit, okay? So type 1 is when one variable or more are solved for. So here's some examples. We're not going to work these ones specifically, but just as some examples of these problems, you might see it where both y's are solved for, right? So in this case, we know that y is equal to both of these. So I could take one of these expressions and plug them in for either y and kind of solve for x that way. Or this is an example of when x is solved for, right? X is by itself. I know x is equal to 2y plus 6, so I could take that x and plug it in for this x down here in the second equation, okay? So let's get some examples under our belt. Let's try one example, system of equations where both y's are solved for in the equation. Let's check this out, okay? So it doesn't matter which one we end up substituting in first. There's really no easier way to do it. We just know that y is equal to both of these. So I'm going to take this y right here, this 4x minus 1, and I'm going to plug it in for the y in the second equation. Okay, so this guy is going to go in for y right there. And so we're going to end up with 4x minus 1 is equal to 2x minus 5. All right. When we do this, though, you notice we have an x on both sides of the equal sign, okay? Both sides of the equal sign. Now, if 4x and 2x were right here, I could just combine them. I could do 4x minus 2x and get 2x, right? But in this case, they're on other sides, so we have to use what we did with literal equations, opposite operations, and we can do it on both sides. So I know these guys are like terms. What I could do is I can undo it here, so I can do the opposite, so that is to subtract 2x. And I can subtract 2x from this side as well, right? I have to anyway to keep it equal. So the 2x is on this side, they'll cancel out to 0, and I get left with negative 5 on the right-hand side. On this side, I get 4x minus 2x, so that gives me 2x and then minus 1. And now I have a two-step equation. 2x minus 1 equals negative 5. Let's think about it with literal equations using SADMAP, right? So we're going to start. Am I adding or subtracting anything on this side with the x? Yes, I am. This minus 1. So I'm going to undo it by doing plus 1 to both sides. And so I end up getting 2x on this side after these cancel equals negative 5 plus 1 is negative 4. And then I go ahead, I divide both sides by 2. And so I get x is equal to negative 2. And so now I have that x is equal to negative 2. Now what I could do is I could plug it in to either of these equations. It does not matter which one. For instance, I'm going to take the second equation. Okay? I'm going to do y is equal to 2 times now negative 2 minus 5. So now we get y is equal to negative 4 minus 5, and so we get y is equal to negative 9. Right? And so if you want to write your answer, we want to write it as an xy coordinate. So I'm going to make that negative 2 comma negative 9, and that'll be my answer. Okay? You'll see that. So when both of these are solved for, it doesn't matter which one you plug in for the other one. Either way, they're going to, both expressions are going to equal each other, and you'll have to solve for x. Okay? I also could have just moved this 4x over. It doesn't really matter. Let's look at this second example. This time, we only have one of our equations solved for y. So this first one right here, we have y equals x plus 9. So that's the one I'm going to plug in for the other y. So I'm going to take that, x plus 9, and yeah, once again, I'm going to plug it in. I'm going to plug it in for my y in my second equation. So I'm going to extend this arrow over here. Yep, because you are y. So now, I'm substituting that entire thing in for y. So I have to keep in parentheses. I have to treat it like it's one y, like it's one quantity, right? So this will become 3x plus 8 times x plus 9, and that's going to equal negative 5. Okay? Now, from here, if you notice, this looks like our distributive property. I have a number that's right next to an expression in parentheses. I can take that number and I can multiply it to both terms here. Okay? So when I multiply, I get 8 times x is 8x, plus 8 times 9 is 72, that equals negative 5. And I'm going to clean this up a bit. 3x plus 8x, that's 11x. I can combine that. And once again, we have another two-step equation, just like we did at this point in this first example. So again, I'm going to subtract 72 from both sides. So minus, okay, a negative 5 minus a 72, that's going to get more negative, so I'm adding those numbers, so I get negative 77. And then when I go ahead, I divide both sides by 11. I'm going to end up getting x is equal to negative 7. Okay? So if x equals negative 7, right there for that one, now I could plug that guy in for either of these equations once again. Make it easier on yourself. Which one would I pick? Probably the top one, because I don't have to multiply the x by anything. I could just literally plug it in exactly as I see it. So instead of x, I'm going to write negative 7 plus 9, and so y is going to equal 2. So my answer is going to be, as an xy pair, it's going to be negative 7 comma 2. And there we go, okay? Let's look at the second type of substitution that you'll run into. So this is type 2. This is when no variables, neither x or y, are solved for yet. Okay, so if you look at this, neither of them are solved for. Sorry guys, I can barely talk today. But they look pretty close to being solved for. This is what we'd have to do. We'd have to use SADMAP to either solve for x or y. You have the choice here. I would also caution you in doing something like this one, this bottom one. While you could totally solve for x with that, no problem. I would pick the easier one. I pick the top one. There's really only one move you'd have to do to get x solved for it, and that is to subtract 6y from both sides. Anytime you see that, pick that one to do. But if you don't, it's not the end of the world, okay? Let's try some more examples, okay? So this is an example where both of them are not solved for. But again, the top one looks like the easier one. This one's easier. Okay, so let's pick that one out and let's work with it. X plus 5y equals 4. I want to solve for x, so I can take that x equals and throw it into the other equation. Okay. Well, I want to get rid of this 5y, so the opposite is to subtract 5y. I do it from both sides. And so I end up getting x is equal to 4 minus 5y, and that is what I'm going to plug in for x in the other equation. Okay, this guy is going to go in here. Alright, so let's see that. I'm going to end up getting 3x, my bad, I already messed up, 3 times x, which is now 4 minus 5y, that's what we plugged in. 3x plus 15y equals negative 1. Alright, once again, we're having to rely on the distributive property. This is going to pop up every now and then when we're doing substitution. Okay? Go 3 times 4, we get 12. 3 times negative 5y, well 3 times negative 5 is negative 15. And then I just plop the y down. Plus 15y equals negative 1. Alright, so far so good. Negative 15 plus 15, that is 0. Huh. Look at that. So 12 is equal to negative 1? Yeah, no, that's not true. That is not true. It's okay that we ended up getting that for our answer, though. Because what this tells us is when we have our equations, when we're doing substitution, when it works out like that, or in this case, if it doesn't work out, then we actually know for this particular problem we have no solution. No solution. We did the math correctly. We did everything we could do. Okay? There is no solution. And that is okay. Sometimes you will run into that. Sometimes you'll run into that with the previous examples that we did. But I wanted to showcase something that you'll see where, hey, if you get something like 12 equals 4 and you know it's not true, you're probably doing it right. It's probably just no solution. And that's all you need to write. You could also write it as this. Okay? Either way is fine. Well, that one didn't work out. But we get the idea of what to do. Solve for the easier variable, plug it in the other one, and then we were on our way to solving for y, just like the other problems. Okay? We would have got that y and plugged it into the other equation, but we didn't need to get that far. Okay? Well, let's look at this one. We have 6x plus 3y equals 54, and then on the bottom, 2x plus y equals 18. Again, both of these guys are not solved for a variable. So pick the one where it's easier to solve for it. I like the bottom one. Again, my argument was with the x, it's kind of just by itself. One move, same with the y. I can get rid of the 2x with one move. What is that move? Well, that move is just going to be subtracting 2x from both sides of the equal sign. And that'll pretty much do it. Let's see. I subtract 2x here. So these cancel here. I'm left with y is equal to 18 minus 2x. That is my new y. Okay, so now in the other equation, I have 6x plus 3y equals 54. Let's take that y I just got, and let's plug it in for this y right here. It's kind of like our bell work, what we've been doing. If a teddy bear is equal to 4, well, that teddy bear is always equal to 4 in that given problem. So we're going to end up with 6x plus 3 times the quantity, which is now 18 minus 2x. And that's going to equal 54. Well, let's go ahead. Let's distribute. We have another instance of that. So I'm going to get 6x plus 3 times 18 is 54. 3 times negative 2x is negative 6x. And that is also equal to 54. Uh-oh. It's happening again, ladies and gentlemen. The 6x's, they will cancel out to 0, and I'm left with 54 equals 54. All right, well, that is true. Okay, that is true. But kind of something similar to what we just encountered up here, right? Except this time we know this is true. When that happens, guys, this is an example of infinite solutions. Okay, something like this, then you're going to have infinite solutions. That means, well, whatever you end up solving for x and y in this equation, it'll work with this equation as well. All right? This is Mr. Knife. Mr. Knife. It's Mr. Knife, not Knight anymore. It's Mr. Knight signing off. Have a great day. We'll see you tomorrow.